Welcome to this lecture series in real analysis. In this lecture, we'll discuss the notions of limit inferior and limit superior. And all we need to know is just the basics of real analysis, what are sequences, and what are convergent sequences. Okay, so let's carry on. Here are some problems for practice. We will make use of this problem at some point, but still I haven't marked it as star. It's a very simple problem, but it may look a bit wordy. You just need to know the definition. So make sure that you know the meaning of what is meant by tends to infinity. It is sort of the same as asking for converging to infinity. It's just that we do not use that phraseology for whatever reason. Okay, so let's move on. So fix a real sequence. Then we can define another sequence out of it. So define for each n the number an, or I shouldn't say the number, but let me write down. It's this entity. This thing, what is the meaning of this? This is more precisely the infimum of that set. So this is a set of real numbers. We are taking its infimum, and this is a very convenient notation for the same thing. Now, this may not be a real number. This could be plus infinite. This could be minus infinite. So this thing is something that lives inside. Let me just maybe note it down somewhere. Maybe I'll write it here. So an lives in, there is no space. Right? An could take values in this set. Okay, we will look at examples, but for now, this is what we can easily notice. So this is a sequence here, and note that it is monotonically increasing. So this is very simple. Note that this sequence is monotonically increasing. Well, of course, under the convention that minus infinite is less than equal to x for all real numbers x, and obviously that minus infinite is less than minus infinite, and that x is less than equal to infinite for all x in reals, and that infinite is less than equal to infinite, and minus infinite is less than equal to infinite. So these are some conventions, some natural conventions, under which we can call this sequence a monotonically increasing sequence. Because when we defined monotonicity, we were defining it only for real numbers, not for sequences which live in this set. So by the way, this is also called the extended real numbers in many textbooks. So this set is also called the extended real numbers. Okay. So monotonicity even makes sense for the extended real sequences. It's a very natural extension of the definition of monotonicity. Fine. So this sequence is a monotonically increasing sequence. All right. And yeah. So what we can do is we can talk about the following. We can talk about this number, limit of this thing. Now this could be minus infinite, or this could be plus infinite, right? Or this could be some real number. So just to expand it out, this is equal to that number, which by notation is written like this. And this is called the limit inferior of the sequence xn. So the limit inferior could be minus infinite, plus infinite, some real number. A priori, we don't know anything about it. All right, so just a definition. Starting with the sequence of real numbers, you can define this thing, which is an element of that set, meaning it is an element of the extended real numbers. Okay. Similarly, you can define this entity completely analogously. Limsup is how we read it. And this is called the limit superior of the sequence xn. Okay. So we extracted two sequences out of a given real sequence. The first is this one, which is taken by considering the infimum of the tail sequences. So once you cut off at, or rather not cut off, but once you throw away all the things before time n, you get a tail sequence, meaning xn, xn plus 1, xn plus 2. That is a tail sequence. Take its infimum, then take the limit. The limit of the infimum is limit inferior. That is how I remember it. Liminf or limit inferior of xn is the limit of the infimums of the tail sequences. Similarly, limit superior or limsup of xn is the limit of the superiors or the supremums of the tail sequences that you obtain out of xn. Alright, so very simple concepts. And let us see some examples before we see any theorems around these notions. So here is our very usual example. This alternates between -1 and +1 according to whether n is odd or even. So what is the infimum of the tail sequence? This is, well, the sequence takes only two values, either +1 or -1, but it takes the value -1 frequently. In fact, it takes the value -1 for each odd time. So therefore, this infimum is -1. Always, for each n, this is -1, which implies the limit inferior of the given sequence is -1. And similarly, you can show that the limit superior is +1. So the limit inferior and the limit superior can disagree. No surprises there. What about this guy? Here, this is a monotonically decreasing sequence. So the infimum, well, not so, but it is easy to see that this entry, this number is actually 0. Right? We have this sequence, this drops down to, visually speaking, drops down to 0. We initially or previously saw that the infimum of all these numbers is actually 0. And the same reasoning shows that this is also 0. So that's fine, and therefore the limit inferior is 0. What about the sequence? This is 1 by m because it is a monotonically decreasing sequence. Sorry, 1 by n. What have I written? 1 by n because we have a monotonically decreasing sequence, which implies limsup is 0. Because limsup is nothing but the limit of these numbers, and that exists, and that is 0. So Liminf and Limsup may not agree. So what am I saying? Liminf and Limsup may agree. In the first example, they did not agree. Now they agree. Okay. And what about this guy? Let's see. So what is infimum of this? This is equal to, well, when m is odd, this number is a negative number with the magnitude equal to the time. So if n is odd, this is -n. If n is even, this is n. So this number is actually -infinite because you're getting smaller and smaller values as time grows. I mean, in any tail sequence, you have arbitrarily small values with arbitrarily large magnitudes, but with a negative sign. So this is actually -infinite, which implies the limit inferior is -infinite. What about this guy? By the same reasoning, this is infinite. In any tail sequence, you have arbitrarily large numbers. So this is infinite for all n, and that therefore the limit superior is plus infinite. And let's take maybe one more example to kind of see all the 4 quote-unquote possibilities. So this time xn equals n for all n. And this time the infimum is n, because it is an increasing sequence. The infimum of these numbers is n, and that implies the Liminf, which is just the limit of these numbers as n approaches infinity. So this is infinity. And it is much more obvious that this is also infinity. So, I mean, we have kind of, here we have some difference between Liminf and Limsup. Here there's a world of difference between them. Here they are equal but at the extended real number. Here they are equal but at a real number. So a lot of possibilities are there. Okay, and one thing I should have said here, that since these are monotonically increasing sequence, I mean this sequence that you get out of considering infimum of the tail, this is a monotonically increasing sequence, but in the extended reals, right? So even in the extended reals, monotonicity makes sense because we have these conventions that minus infinity is less than equal to x, etc. So this is a monotonically increasing sequence. So this thing actually makes sense. Okay. So if these numbers were, let's say, all minus infinite, then this limit is declared to be minus infinite. So again, I don't want to lay down all the details here, but the obvious things that you think are correct. Okay. Fine. So here is a very simple fact that Liminf of any real sequence will always be less than equal to the Limsup of the sequence. Again, under the conventions that minus infinity is less than equal to x for all real x, and x is less than equal to infinity for all real x, and minus infinity is less than infinity, and minus infinity that is less than equal to minus infinity, infinity is less than equal to infinity, etc. So the natural conventions, under those natural conventions, we are stating this. Okay, so why is this true? So let an equals the infimum of the tail starting at n, and bn be the supremum of the tail starting at n. And note that this is the case for all n. And from here it just immediately follows that this is the case. Why? Because these things both make sense. Okay? So if both of them were convergent sequences, then this was clear, but one may be tending to minus infinite, etc. So one has to just maybe make some cases, that's all. And this is where you can also look at the third problem that we gave in the beginning of the lecture. The third problem in that problem sheet is exactly about this. It was in fact a little bit more general, because here we have these are increasing and these are decreasing. There we don't even need that. Okay, so this is very, very simple. And now here is the most important thing in this lecture, that if we have a bounded sequence of real numbers, then the sequence is convergent if and only if the limit inferior agrees with the limit superior. Okay? So the notion of convergence has yet another equivalent formulation. We earlier saw the formulation in terms of Cauchy sequences. Here we have another formulation in terms of the limit inferior and limit superior. So limit superior is kind of one way to look at how far above the sequence goes, and this is one way to look at how far below the sequence goes in some sense. And if those two values agree, the sequence is tamed at a particular value. I'm saying something very airy, philosophical kind of remarks. Okay. So let's prove it. It's not hard. It's basically an exercise. So first assume that we have a convergent sequence. So suppose our sequence converges to x. We want to show that the limit inferior is equal to the limit superior. Okay. So then for all epsilon greater than 0, or maybe it's better to just fix an epsilon. So fix an epsilon greater than 0. Then we have, in particular, I mean, this thing implies in particular that xn is less than x plus epsilon ultimately. Right? Which means, or which implies, not means, but implies that the supremum of the tail starting at n is at most x plus epsilon. So note that there is a less than equal to sign rather than just a less than sign. Right? This is happening ultimately for all n. Right? So just convince yourself that this implies that. And therefore, it follows that if you take the limit, then the same thing holds. And that's it. This is same as the limit superior. So the limit superior is this much. Similarly, one can, so let me maybe record. What we have shown so far is that the limit superior is here, and this is always there. Limit inferior is always dominated by the limit superior, which by the same kind of reasoning gives us this. So we have established this, but this is true for all epsilon greater than 0, and therefore these two numbers must become equal. Here I forgot to write xn. Yeah. So these two numbers must be equal because this happens for each epsilon greater than 0. Okay, so this finishes the proof in this direction, meaning if you assume convergence, you have proven the equality of the inferior and the superiors. For the other direction, assume the two limits agree. This is equal to x, and x has to be a real number. Why? Because we have a bounded sequence. If you have a bounded sequence, this thing cannot be minus infinite or plus infinite or anything, and same for this. Both of them have to be real numbers, and therefore x is a real number. It's not some extended real number. Okay, so let's just look at the second one. Looking at this one, call it star. By star, we have, again fix some epsilon greater than 0. By star, we have this supremum starting at, supremum of the tail starting at n is less than x plus epsilon ultimately. Why? Because what does star mean? Star means that this sequence, as you vary n, this is a sequence, this sequence converges to x, right? So this happens ultimately. Okay, which implies in particular that xn is less than x plus epsilon ultimately, because this number dominates xn. So we have that, and similarly, if you exploit this condition, you will see that this happens ultimately, and that establishes the convergence of the sequence xn. Because this happens ultimately and this happens ultimately implies that these two happen simultaneously ultimately, and that's it. That is true for each epsilon, and hence we have convergence of the sequence xn. Okay, so here we proved something for bounded sequences, but you can massage the statement to get a analogous statement for not necessarily bounded sequences. So this is a real sequence, then this is infinite if and only if there is a subsequence which tends to infinite. Okay, and similarly, a similar statement for limit inferior, and you can easily prove this. So this I leave as an exercise. Okay, so next lecture we will look at the notions of limit inferior and limit superior in a different light. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.